Good morning, everyone. My name is Shunsuke Sakura. Today in this presentation, I'm talking about fluctuations in natural gas hydrate production, specifically hydrate blockage in water dominant systems. I'm PhD, but I submitted my thesis. I studied fluctuations of gas hydrate in water dominant system. But previously, I worked as fluctuations engineer in Japan. And now I'm interested in gas hydrate in chlorine, the level of hydrate slurries, and natural gas hydrate. So in this work, we conducted a flow loop experiment, and we observed gas-state hydrate slurries during certain operations. And the gas-state hydrate slurries became more rigid at higher hydrate volume fractions, but it wasn't affected by a certain period. And we also observed hydrate plugging during restart operations at high hydrogen volume fraction. This work used hydrate aggregation loop at oil field technology. And the key feature of this flow loop is an inline video camera located installed to here. And this enables us to observe bubbles or hydrate particles in flowing water. So in natural gas hydrate production, produced liquid is water. This means no liquid hydrocarbon phase. And this is different from the systems in conventional productions. But this system hasn't been well understood. And it's a basic motivation of this study. And in general, plugging mechanism depends on dominant phase. And for instance, in conventional oil production, there are two mechanisms, oil dominant and water dominant. And in oil dominant system, water is dispersed in continuous oil phase and hydrate forms at the surface of water droplets in oil phase. And formed hydrate may create large aggregates, and large aggregates may cause plugging. But in water dominant system, gas and water are dispersed in water, and hydrates should form at the interfaces between gas and water, and formed hydrate may cause agglomeration and plugging. And water dominant system may have some similarity to the pure water system, but may have some differences, such as efficiency of AAs because of the absence of the interface between oil and water phases. And so before moving into the details of water dominant system, pure water system, I'll briefly explain the natural gas hydrate. And natural gas hydrates are regarded as potentially future energy resource because it's abundant in nature. And there exist under deep water or permafrost because they are stable under high pressure and low temperature conditions. And natural gas hydrates are categorized by the locations and sediment types. And at present, gas hydrates in sandy layers are regarded as most promising. And the field tests were actually conducted to demonstrate gas production from these hydrates. However, these production tests suggest fluorescence risks in production. For example, in the offshore production with depressurization method, gas hydrate in reservoirs are dissociated in situ by reducing the downfall pressure by pumping water from the wellbore. But if gas is entering into the water production line, hydrate may be formed in the water production line because of the high pressure and low temperature conditions. So, and it's considered that there are three steps in the process leading to hydrate plugging. So hydrate growth, agglomeration, and plugging. And our challenges to hydrate growth and agglomeration were already reported in previous symposiums. And today, I'd like to talk about our challenge to the first step, plugging, which may be related to the loss of fluidity of hydrate slurries during shut-ins. And key concept of this study is hydrate slurries are viscoelastic materials, and so which have two states, Zol and Gel. And these two states can be explained by the distribution of the solid phase hydrate particles. And in Zol state, hydrate particles dispersed in liquid phase. But in Gale state, hydrate particles should form a continuous network structure like this one, which is a source of the elastic behavior of hydrate slurries. For example, so if you apply the stress to this material, particles in the structure should be displaced or deformed. And this behavior should store the energy inputted by the applied stress. And the driving force from Zol to Gale is coefficient force between hydrate particles, and that from Gale to Zol is external stress. And for instance, if you gradually increase the applied stress, the structure is eventually broken at some point. And the stress at this point, roughly speaking, is called yield stress, roughly speaking. And in previous, many studies discuss the Zol state hydrate slurry, which correspond to the steady state productions. But a few studies examine the Gale state hydrate slurries. But if you want to discuss shuttling operations, you need to consider this state. And so this is a basic framework of this study. And this framework tells us the importance of studying the Gale state hydrate slurries. And so in this work, we investigated Gale transition of hydrate slurries from shuttling to restart by visual observation of hydrate slurries and the measurement of critical stress for flow restart with a flow loop. So this is a flow loop used in this study called Hydrate Aggregation loop. And key equipment of this flow loop in this work is a flow meter, a differential pressure gauge installed to a horizontal section, and an inline video camera. So in experiment, first we inject water and small volume methane into the flow loop outside the hydrate stability regions, and then reduce temperature to 3 degrees. So in this step, PT conditions enters the hydrate stability regions. So hydrate formation begins in this step. And this step corresponds to the regions highlighted in gray in these graphs. And after that, measure the critical stress after 3 minutes and 8-hour shuttlings. And then inject a certain volume of gas into the flow loop to increase the hydrogen volume fractions. And repeat step 3 and step 4 up to about 20 volume percent of hydrate. And in this work, the critical stress is defined as the wall shear stress at flow restart or flow stop. And so critical stress can be calculated from the pressure drop in a horizontal section. And this is a procedure of the measurement. First, we decrease the flow rate stepwise by changing the pop rotations. And eventually, the flow was stopped. And we check the delta P at this point to estimate the critical stress at flow stop. And then turn off the circulation pump for shuttling. And this example is 3-minute shuttling, so waited for 3 minutes in this case. After that, we started to increase pump rotations stepwise. And during this period, the delta P was gradually increased, but flow rate stayed 0. But at this point, the flow rate was suddenly increased. And so we checked the delta P at this point to estimate the critical stress at flow restart. First, I'll introduce our data of hydrate slurries, Gale state hydrate slurries during shuttling operations. So these are photos of hydrate slurries at the beginning of 8-hour shuttlings. So at 2.6 volume percent, there are void spaces. But at 5.2 volume percent, hydrate particles look to occupy the entire space. And in addition, at 2.6 volume percent, the critical stress for flow restart wasn't observed. But at 5.2 volume percent, the critical stress was observed. So this suggests the Gale state hydrate slurries during shuttling periods at least above about 5 volume percent of hydrate. And this trend is similar to that in oil dominance system. So this is a data of hydrate slurries made from water in oil emulsion in a rare metal. And so in this case, the yield stress was observed at, only at 5% of initial water cut. And so this is a relationship between critical stress and hydrogen volume fractions. So overall, critical stress increased with an increase in the hydrogen volume fractions. And again, the critical stress wasn't observed at low hydrogen volume fractions, but at least above 5%, the critical stress was observed in all the measurements. And we tested two types of restart operations, slow linear, green line, and quick restart, purple lines. But these operations didn't affect the critical stress, at least in our measurements. And these three symbols correspond to three experimental runs. And there was a clear difference between the critical stress before and after 3-minute shut-ins. However, there wasn't a clear difference between the critical stress after 3-minute shut-in and after 8-hour shut-ins. So the data are overlapped in this graph. So this means, this overlap means no effect of shut-in period. But interestingly, this trend is different from the trend in oil dominance system. So in oil dominance system, the yield stress increases with shut-in time. So this is an example. So it's a yield stress of hydrate slurries made from water in oil emulsion in a rare metal. So in this case, yield stress increased in the first 8 hours, and then it stayed constant. So this trend is completely different from ours. However, this trend, this difference may be explained by the microscopic view of hydrate slurries. So in theory, yield stress should be a function of the number of contacts, so indicated by red bars, and strength of contacts. But during shut-in operations, number of contacts shouldn't be changed significantly. So yield stress during shut-in may be explained by the function of the strength of contact. And strength of contact may correspond to the cohesive force between hydrate particles. And the right figure shows the cohesive force between two contacted cyclopentane hydrate particles. And in this data, the cohesive force stayed constant in the first 30 seconds. But after that, it started to increase because of the hydrate sintering at the contact point. And so these results suggest the microscopic view may connect the increase in yield stress to the increase in cohesive force. And this framework raises a question to our result. So did hydrate sintering occur in our experiment? So I checked our result, and these are photos of hydrate slurries before and after 8-hour shut-ins at 16% of hydrate. And in these figures, there's little gas bubbles, suggesting little hydrate sintering. And so little hydrate sintering, due to lack of gas molecules, should result in the little change in strength of contacts, and this may result in no effect of shut-in period in our result in pure water system. And another interesting finding is that the critical stress is a power law function of the hydrogen volume fractions. So this is a critical stress data already shown in previous slide. And if you take the logarithm, you can find that the data are on the straight lines in log-log plots. And this linear relationship indicates that the critical stress is a function of the hydrate volume fractions. And this expression is the same as the equation of the yield stress of general suspension derived from classical model. And dF in this equation is a fractal dimension. which represent how porous the network structure is. And in addition, this equation can be mathematically transformed like this. And this equation suggests that the fractal dimension may be estimated from the slopes of the fitting lines in our data. And in our data, the fractal dimension became 2.21 and 2.26 with respect to the critical stress after 3-minute shuttering and after 8-hour shutterings. Next, I'll introduce our result of Hydrate plugging and a bit discuss the plugging mechanism during restart operations in pure water systems. So at 18 volume% Hydrate, it failed to restart flow with a slow linear increase in pump power, pump rotations. And this orange line indicates a pressure drop in this horizontal section. And these 5 photos are taken at these 5 periods. And so in this case, in the period from A to B, the Hydrate slurry was gel state. So slurry was slightly moved, but the arrangement of particles was kept during this period. But at point C, the structure was broken. And immediately after that, the delta P was steeply increased. And around the peak at point D, the Hydrate particles disappeared from the observation region temporarily. And then delta P was sharply dropped. And immediately after that, flow was restarted, but flow rate was quite low, less than 1 centimeter per second. And so we weren't able to increase the flow rate anymore, even though we set the pump power to the maximum. So we gave up to continue the experiment in this case. And important things in this experiment is that the Hydrate plugging was happened after yielding, considering these 2 events. And interestingly, so we succeeded to restart flow with a quick increase in pump power at 19.3 volume% of Hydrate. So in this case, flow was restarted at this point. And in the period from A to B, the state of slurry was gel. But at this point, the state was changed from gel to zero in a very short period. I'll show the video at the point of restart. So the state was gel at this point, but it changed immediately from gel to zero in this case. And so these different results with different pump operations suggest restart procedure affects the plugging potential, and rapid restart operation may reduce the plugging risk during restart operations in pure water systems. And in terms of the different results with the different pump operation and the plugging mechanism, these may be related to the large aggregates stuck to somewhere in flow line. So after yielding, continuous network structure may be broken into large aggregates like this one and many small Hydrate particles. And large aggregates may stuck to somewhere in flow lines. And if this happens, small Hydrate particles may be trapped at this point. And this may result in the higher local hydrogen volume fraction, and this may cause the Hydrate plugging. But if you apply quick restart operations, large Hydrate aggregates like this may be broken immediately, relatively short with short period, and before the accumulation of Hydrate particles at this point. And if this happens, so Hydrate plugging may not be occurred. So in this work, in conclusion, the flow loop experiment was conducted, and the hydrate slurries turned to gel state during shuttering operations after above about 500% of hydrates. So we observed development of continuous network structure of hydrate particles and the critical stress required for flow restart. And the gel state hydrate slurries became more rigid at higher hydrate volume fractions, but it was independent of shuttering period. And there was power law relation between the hydrate volume fraction and the strength rate. And hydrate plugging was also observed during restart operations. But it happened after initial easing. And this type of plugging may be avoidable by rapid restart operations. Finally, so this study was conducted as a part of the program of MS21S R&D Consortium, funded by the Ministry of Economy, Trade and Industry. And I also express my gratitude to Jogmek, Oilfield Technology, especially Ben Joy, and Bruce and supervisors of UWA.